So we are into our third week and third week's first lecture. So probably you can see these numberings over here, and this lecture is going to be something like systems approach, and in the first lecture we will be introducing the topic. Maybe in one way we can say systems of prognostics and health management and a systems approach is unique to this lecture, because so far whatever publications or work you would have seen that deals PHM at component level, okay, and maybe in some cases failure mode mechanism and effect analysis has been used, but then when you talk of the complexity of the system, maybe at component level knowing mechanism, mode and all is good, but when it comes to system level you require a holistic and integrated approach. And now today we will be introducing this topic, that is systems approach in this lecture. I mean, first let's look at this image. What we say system means. In fact, a plant can have many systems, okay, and these systems together, maybe some of them they are process system which are used to delivery of the system. That means this system they operate and the plant's output targets are met. But in case anything wrong or any deviation, then there are some systems which are called safety system, which remain passive during normal operation and they get activated. And this activation comes because there is some correction mechanism is required in the plant, or there is some deviation which is happening and they need to be controlled on urgent basis. And then if the accident happens, it helps reduce the consequences. If not could not control it, then it is the mitigation measure that safety system they provide actually. So now let's see the outline of this lecture comprising of 10 plus slides. What do we mean by system? Okay, so any system you see it requires a modeling. If the system is existing, it requires a modeling, but when you are at the design stage, it helps you to work out the design aspect and of course safety aspect of the system. So what are the modeling requirement? I mean, we should understand why we should model and what deliverables we are expecting from the system. So that, and then system performance metrics in the sense that whether it is risk, whether it is reliability, whether it is safety, whether it is security. I mean, those kind of things we should know. I mean, we will be discussing on the separate slide this aspect, and then procedural steps that are involved in a system, broad procedural steps. Slowly we are going into the details of system modeling. So there you will see, and then the other lectures, they are basically system modeling approaches that we will be discussing, and then we will have a statistics and probability in relation to PRA, okay, and then probabilistic distribution. Probabilistic distributions are at the core of probabilistic modeling. Why? Because data determines the quality of the analysis, and for determining the correctness of the data or adequacy of the data, validation measures are required, and probability distribution is one of the stages where it tells the how accurately we are able to model the system. Okay, one more point which I was trying to insist. There are two considerations when I use the word system here. It means one is system is, I can call this is an energy system, nuclear energy system. Okay, so this also we can call it, actually we call it as a plant. Okay, so sometimes plant and system they are used as a sort of describing one thing, that is a plant in general, and then second thing is system means this plant is made of so many systems, it could be process system, safety system and all. So there also we use the word systems. So systems approach, when I say, it is basically, it means a plant's approach. So in a plant, how PHM should be implemented based on the identification and prioritization program. So that is where we call systems approach. But when it comes to system modeling, we say safety system modeling or process system modeling. So I think you need to distinguish between these two when this term system is used all through this presentation. Okay. So now when we call system modeling objective, I mean when we are having reliability modeling. Now in reliability, like if you talk about the space system, there we focus on basically mission reliability. Okay. So mission reliability and mission risk. So this is called mission reliability. But then in other systems where there is a continuous operation of the system and they are operating over an extended period of time and providing the deliverables, whether it is power, energy, or some product or services, then it is called operations reliability. Okay. And then of course safety is one of the overriding metrics. I am using this word again and again just because I want you to understand, before reliability or any other metrics, safety metrics takes over, and it tells us what is the safety of the plant, and it is non-negotiable component actually. Okay. Then we have a now new component here, that is system security risk. Okay. And that way, if you see the probabilistic safety and security, even though they are modeled separately, but then there is a good overlapping over there. Almost like same tools they are used for modeling and security risk and safety risk. But then we have to distinguish between overlapping areas and an independent area dedicated to security or safety. But safety now covers the plant operational safety and security safety, both. So that way these two have to be understood because now security is becoming slowly important aspect of safety analysis. Next is system availability. Often in individual system in a plant there are so many systems are there, especially safety system. So there we want to assess the plant availability. In fact, the availability aspect is presented maybe using bar chart and all for many years. What was the availability of the plant and all that? So that also, that means what was the availability factor during the year for a plant, and if I plot say 10, 20, 30 years, I will know, and these charts are very important because you want to know what is the status of the plant, whether it is operating at full capacity or whether it is operating at 80% capacity or whether it is operating at 50% capacity. If it is operating at 50% capacity, how the capacity factor has dropped, and probably it might be an indication of the plant aging after 20, 30 years or so. So system availability also provides a very good metrics. Of course, it is one of the spin-off of probabilistic risk assessment, or use similar methods, and the way we use it in at plant level, this risk and all that. So similarly, unavailability use, in fact, this unavailability or availability, it is a part of safety system modeling. When we solve a fault tree and then top event, the top event inherently will be unavailability. That means 1 minus availability. So availability of the plant is important even when we do safety system analysis. And then last is quality assurance. We will be introducing the quality assurance because if the analysis is not having quality, then it doesn't serve the purpose. Rather, it cannot be used for practical application. So this is a very important aspect. We will be discussing in brief, and as and when we go ahead and all, we will be discussing other aspects also. System modeling requirement metrics. When we model a system, since now this is an era of computerization and all that, integration becomes a very important attribute of any system modeling. That means all the aspects with their importance apportioned, they are brought to one level, and finally when you get the risk estimate, you get even other assessment also. So and of course for analysis and understanding also, right from the root that is basic component of the plant to top level of the plant, all the components should be shown in a relation to each other, how they are operating. Okay, and what happens if one component fail, then how it affects the system and eventually the plant. So what we need is an integrated approach, integrated framework. And one of the quality of the probabilistic risk assessment, which takes it a major importance, is integration. And then the quantified model for the quantified output. Actually qualitative metrics, they work up to certain limit, but then when the complexity of the plant, like for complex engineering systems like energy system, space system and railways, then the quantified metrics is required, because even if I want to say one component is more reliable than the other component, if I do not have a quantified metrics, if their performance is very close by, I cannot distinguish between them. Point number one. Point number two is, even for identification of a system for its maintenance or for operation, we require a quantitative metrics. Why? Because if we can cover in quantitative metrics, whether it is maintenance, 20% of the component, it addresses almost 80% of the issues that we are facing. So that is the effectiveness when we have a quantified system. And quantified system means inherently it is a rational based system. So that is the most important thing over here. And then we need database also. Of course, when a plant is in design stage, you will not have plant specific database. So the initial analysis is performed using generic data. But then are some plant which is similar to this plant, we take the value. Of course, it is analyst's choice which data he wants to use. But in design stage, there are not many options, because we have to use data and we have to show where we stand. And this design stage studies, they are performed for optimization purpose of the design. So they are very critical in that sense. So in absolute sense, it may not be very important, but in relative sense, it becomes a quantitative analysis is required. And then along with the statistics, as of now, most of the tools, they are operating in a static tool. But then if you want it to be more effective, then dynamic modeling is required. And of course, even in the static era also, there are many tools like Markov models, not PERT actually. There are some tools which can be used, like Markov model can tell us, it can occupy, it can address more than, like fault tree and all, they have only component is either success or failed, standby or failed. So but then in Markov we can have many status, especially if it is important when we want to go for fault tolerant modeling. So partial failure, full failure and all that, if you want to do with maintenance, without maintenance, Markov modeling helps us a lot. Then accounting for uncertainty. This is the most important attribute when we go for any system modeling, that uncertainty. Of course, it is known that all the uncertainty, because aleatory uncertainty, it comes with the system, it cannot be reduced further. But epistemic uncertainty, it can be addressed. So if we have uncertainty statement, we would be, at least at the outset, we will know whether how far we can believe this data, whether it is a completely dependable data, or it is something like we cannot depend on some more testing or thing. So probably this insights are available from uncertainty analysis. Then facilitation of risk identification. Okay, so this is, we know that in risk model, risk identification and prioritization, those things occur. And these very model, they require optimization of the core metrics. So if these characteristics are not there, and then if we talk in terms of capability, if we want to be accurate, then these following aspects need to be answered. It's called common cause failure, yes. because we will be showing in the subsequent presentation that how important it is. If we do not take into account common cause failure, then the result could be over optimistic, okay, and it might not give correct estimate. Two components which are redundant component, if I multiply their independent probabilities, it will give, let's say if I assume 10 to the power minus 3, so two component redundant, their failure probability of the system that they are comprising, it gives 10 to the power minus 6. Now if I use common cause factor, it might come to 10 to the power minus 4 or 10 to the power 5, but definitely it will not be 10 to the power minus 6, depending on what common cause factor we have taken. So this is, and then human factor or human reliability data, they come with relatively larger uncertainties. So we have to straighten our procedure, methods and calculation models to reduce the uncertainty. Maybe it might require some simulator experiment, maybe it will require some more credible data and all, but uncertainty has to be within acceptable limit. And if I do talk in terms of long normal distribution, error factor, it should be less than 3. So that is the desirable thing. But if it is around 3, then also it is acceptable. Importance measure. Importance measure is critical because there are 3 or 4 importance measures are there in risk assessment or reliability assessment. We have to use it and we have to prioritize the system. Why? Because even from safety point of view and from plant economics point of view, it works actually. I know these are the 10% component which are very important, which will solve my 80% problem. This sentence itself is so effective. Knowing the importance, it really works for safety and security as well as for our deliverables also. Time and space, various important measures, they keep changing and all that, so that we have to address. Availability of a professional and benchmark software. This can never be more underlined, because if software is all this exercise that we are talking about, they require complex software actually. So a benchmark software is required, so that later on we don't face problem because due to accuracy metrics or so many other issues, uncertainty metrics. So a well known and benchmark software, if it is not benchmark, we have to run some cases and benchmark the software. Now when we talk about the risk metrics, probably we, in some way or other we have discussed. So the major risk and reliability metrics are, one is probabilistic assessment. When we talk about it, the plant level PRA, actually we are discussing level 1 PRA, that means system analysis, which is applicable to all the plants. Level 2 and level 3, they are more relevant to nuclear plant, because there is a containment, and what is happening inside the containment, that is one thing that level 2 addresses, and what is happening in the public domain, that. But if there is no containment, then it is level 1, that means system analysis, and public domain, that is level 3 they happen. And we are because we are talking about the risk and reliability and all, much can be done at system level 1 system only. So that's why we are talking about level 1 probabilistic risk assessment. So system level, system unavailability is a very important matrix. Normally if we refer our standards, that is engineering standards, you will find that the system failure probability, unavailability should be less than 10 to the power minus 3. So that means once the benchmark is available, we have to bring our system in matching this thing. And process system initiating event frequency, they are basically like loss of offsite power. It is site specific condition, but what kind of provisions have been made in the plant to address if the initiating event frequency is more or less. In that sense, it is one of the important metrics. Statement of core damage frequency. Let us see this, we are talking core damage frequency. It is used in respect of nuclear power plant, but if I remove core word, damage frequency, damage beyond a limit where the plant cannot be brought back, or it is impossible to bring back the plant from the damage condition. So it is called core damage frequency. Okay. And the core damage probability, of course, if I have some certain issues to be prioritized, identified now, then I use core damage probability. It is more of academic interest, but this core damage frequency, I can compare two plants, similar plants. what are the system performance, what are the initiating event frequencies. So, it provides a very integrated and holistic metrics there which enables our selection. If I have to select between two plants, taking into account the uncertainties involved in all that, I can take a decision, and this decision will be called as risk informed decision, because already you are reaching certain decision, you got a risk input, and then you took that decision. Then decision matrix. Decision matrix is something like, we will see later, but then it gives us if these two things happen, then what happens. Okay, so it is called the parameters which are there, and then consequences. Okay, so normally it is referred as if and then rule, or any other algorithm. And then we have a risk achievement worth and risk reduction worth. These are the metrics that we use while testing components, and there we are trying to see the testing frequency and all that. So we will be discussing this later on. Maybe not in this lecture, but sometime when we do really as part of system approach, we do the identification and prioritization. Then containment level 2, and then containment level 3 risk matrix. Containment level 2 is release frequency it is for a nuclear plant. Okay, but it is this particular matrix becomes the final matrix for any other chemical process plant and all that. And then finally, what happens in the public domain, this becomes the matrix. So, the containment word comes because inside the containment, but if there is no containment, then similar matrix becomes here for level 3 actually. Now, data requirement. Data requirement can never be emphasized, because data determines the quality of the analysis that we do. And if my experience is there on risk modeling and all that, huge effort to the extent of around 70% goes into the data collection, data analysis, and data elicitation. These things have to be met. It is not that simply you created some data, it has to be benchmarked also, and it has to be compared with some other systems also. And the rationale why in some database data is more showing less unavailability compared to the system that we are dealing in, what are the issue. In fact, this itself can become a one of the platform for root cause analysis. And then there are 4 major source of data sets. I think we should remember. One is plant specific. This is ideal. If I am doing some analysis for certain plant, my data should be plant specific. So this is applicable for operating plants. If a plant has seen something like any risk analysis or probabilistic risk assessment, it start with even during the site selection itself. But then, because we have to see the public domain and its influence if some consequences are there. So, but then it goes to the design stage, then it goes to operation stage, it enters into operation also for certain application, and finally when the plant has gone aging, then we have to see what is the risk level and unavailability level. And so, but then plant specific data becomes very important. Of course, during design stage there is no option, plant is not running, so we have to depend on generic data or data from any other similar sources. So that we have to manage, and as the plant operation comes starts, and we have accumulated experience in couple of years, starting from 1 year to 5 years, 10 years, and we can keep upgrading the model. Then handbook, this is more true for electronic components and all that, because at component level, at card level, what are their estimation that we, so handbook facilitates a very good mechanism. Of course, now Meal Handbook 217 was plus has come. Earlier Meal Handbook 217 was there, but then there were doubts regarding whether it is good or adequate. So the physics of failure methods have come. So a lot of advancement has taken place. So either you can call POF at lab scale or at a plant level, advanced plant level, or handbook approach we can use. expert opinion, fuzzy logic approach can be used if the qualitative input is there, and of course then because fuzzy approach is used where the input is imprecise, like a opinion of an expert, okay, or we are talking in terms of high, low, very high. These are all qualitative opinion, and the fuzzy logic enables transformation of this into quantitative metrics. Plant specific sources data should be preferred, we have discussed, and the a computerized data system is required if we are going for a big plant or mega plant, the risk assessment or system modeling, then it is not an option, it is required. Applicability could be have its focus on system approach. See, it first is site selection itself. If a systems approach is there, it can help in site selection. Then system model selection. What system we should build, what kind of redundancy is required, what kind of component that we use, what should be the quality criteria. So there it helps in system modeling. A component which is having higher risk significance or safety significance will require higher quality, and then we have to use codes and standards, no waiver. But suppose if it is a service system, we can little bit, because it doesn't directly affect the plant immediately. So like that we can have those things. Then design requirements. This helps in our model. It helps. What are the design requirement? That means, let us, if I talk about the one parameter, what is the failure criteria for the system? That can be made up, of course, design output, deterministic output form part of it. But then if you have to fine tune the condition in terms of mission time, how long it should operate to meet this, and what kind of uncertainties levels are required, then design details are, and design details other than the structural and thermal hydraulic parameter, if probabilistic parameters are there, design becomes more robust. Operational management, in fact PRA can extensively be used for operational management, whether it is a maintenance management. When I talk operation, maintenance is explicitly their part of the operation. So maintenance management, then in service inspection that we do, it's a timing, it's a frequency, when it should be done, and whether frequency can be increased or decreased, those kind of things. And finally we come to the stage of refurbishment. If my plant is going after 30-40 years of operation, if it is entering the aging period, how aging should be performed, and plant can be restarted with a new mission of, let's say, 10 years, 15 years, 20 years. There are publication in this area, and end of life decision. Finally, the life has to end. So, and then end of life, when we talk about it, what could be the disposable management, hazard management, these kind of things also, because we have integrated model, it can be done. And of course, it is very popular in regulatory review. It's called risk informed decisions. Many complex situations, they require of course risk is part of all processing and everything, but often the risk or safety insights, they help solving or they addressing the decisions in regulatory ecosystem. So let us see what are the major steps in system approach. This particular steps I have kept in mind, they are related to probabilistic risk assessment, but for other things also it is similar steps are there. Model methods might change, approach might change, but this, like suppose what are the events affecting my plant? Loss of offset power, it is seismic event, or it is some accident situation. So a list of this will lead to formulation of a list of accident, and the major tools are plant logic diagram, plant specific and data, and then similar plant sources, generic sources. So from these sources we can obtain their frequency, and we have to see that they are justified for our plant. I can take a data from other source, but then if I talk my plant specific source frequency is not in agreement, I should use my own plant source frequency even if data is less, and go on updating this data so that we come to the realistic estimate. Inventory modeling. The inventory, so initiating event and the next stage is inventory modeling. It is a qualitative modeling actually. So we use the tool fault tree, in fact inventory modeling and Markov models. These are the tools we use for inventory modeling. So I would say prominently inventories are used for inventory modeling, and Markov models and all to support certain frequency. If you want to adopt with maintenance, without maintenance, a complex situation, then we use it. And fault tree mostly they are used for system modeling. So then fault tree modeling means now I know my plant, and now I am trying to model the plant using the available data that might include manuals, information. Then I make site visit, then you see the drawings, and then I create the fault tree. So here inventory will be little less, but Markov model will be extensively used for fault tree modeling. Fault tree modeling and Markov model, they are different, but fault tree alone 90% of the time it is used for system modeling. Actually it should be event modeling and system modeling. So these tools can be used. Then qualitative analysis. So based on this, whatever we got, we get the qualitative analysis for generation of accident sequences. Okay, accident sequences at generation level, and then at the system level it will give us unavailability estimate also. Okay, so minimal cut set at unavailability level, and for plant level accident sequences will get here. So now so far what we got is qualitative input over here. Then data collection, quantification. So for estimation, hardware, software and human reliability estimates actually, and then the plant model that was created, it is quantified. So accident frequency and plant risk, that will come into picture, and of course system unavailability also will be part of it. And then once we have with this one, then we get the uncertainty and importance analysis. In fact, if we do in computerized environment, this system, then the component itself is characterized with uncertainty or error factor, which is called error factor. So there since the component is having the uncertainty associated with it, the top event, that is unavailability, and subsequently at plant level also we get uncertainty safety. But then importance analysis requires certain more simulation, sensitivity analysis, because when we create the plant, a lot of assumptions are made, and these assumptions have to be validated. They might be correct also, but it has to be validated on the model. So it is called sensitivity analysis. We choose the parameters which test the model and its applicability. Then finalization of the document. This is the last stage. Once the document is issued, then developed, then it is a draft document issued for comments, and final document is issued to the external agencies. So as I mentioned, there are codes and standards are required, because if I have created a model and I am approaching a let's say a regulatory body, there can be a question, or there will be a question, which standard it is meeting the criteria. Okay, so it could be a quality standard, it could be development standard. So there are some International Atomic Energy Agency for nuclear systems, they have this standard SSG 3 for level 1 PSA, and SSG 4 for level 2 PSA, and then 8, I think old version 8 is for 12 is for level 3 PSA. Then addendum ASME, this is a very large early release frequency, and their years are also given. So you can see there are many standards that are available. ASME, ANS, RAS this standard for level 2 PRA for light water reactor, then ASME. So this mostly we are talking about nuclear standard, but a respective domain can have their own standards, and then we can see how it is our analysis is mapping. Like there can be one question, how often you use generic data, what proportion of plant specific data we have used. If I say 50%, that means it gives certain evaluation. If I say 80%, or if I say 100% is not possible, even if it is used 80%, it is justified, because some data comes from generic sources. That could be because of new component or so many situations, you know. So, and then the quality attributes. Quality attributes are very important because it determines the in standard, and there are some standard they are built on for quality only. So, their matrix is given, like working group should be you know, having all sorts of expertise to build the model. Then defining objective and scope, it should be very crisp and very clear about the system. Then quality conformance, how far quality conformance program has been met for which system, which component, and there are some IAA tech doc and ASME tech doc which you saw in the previous slide, they are available. And plants and schedules, what are the schedule chart and all those things, they form part of the quality of a PRA model. Establishment of criteria and technical requirements. So, these like failure criteria, it should be very crisply designed. Technical requirements, what kind of components we are buying, what are the quality standards, and what is our quality assurance program during the things. All those things should be mapped out when the report is for the project report is issued for a PRA. So, this determines the quality of projected PRA model of the plant. Okay. Now, then once the study is done, then there should be multi-tier review. It not only internal, it should be subjected to external review also, that might include even the regulators. And then input in support of PRA. Provision should be made in QA program to ensure that the input from outside of the PRA, for example, plant design operation data, which includes thermal hydraulic and core, all these things should be addressed in this one, and their testing level and their accuracy level has to be. And finally, again this also boils down to the success criteria and quality criteria. Verification and validation of computer code, that we have discussed in the previous slide. Uncertainty and sensitivity analysis also we have discussed, and documentation. So, these are the things when the project report is issued, there should be a plan what quality criteria we are meeting actually. So, in this lecture we saw systems approach, introduction, then development of a PRA model in fundamental to optimized model of a PHM. So, there are many approaches, we will see in the next slide, but then we have done a study how PRA for a complex system can fulfill all the individual approaches objective. So, that is why we are talking about the optimization modeling of major approaches to system modeling. That also we will be discussing in the next slide, and here we have discussed some fault tree, event tree, analysis and all, but that will be expanded in the next lecture. Major procedural steps that we have seen in PRA. So, you will find that the knowledge about the systems approach or systems modeling is scattered all through this lecture on prognostics and health management systems approach, because sometimes like sensor, it requires a separate section, data acquisition system, it requires a separate section, system modeling, it requires how the data is built, how is reliability estimates are derived. So, those kind of things. Systems approach will run along with this lecture. Now, like for example, as of now we have not discussed in this lecture, that is lecture 3, the risk importance of the component. That will be demonstrated when we create a list of identification and prioritization. Major procedural steps are there that we have discussed.